of government is bad. People in the AI community refer to the advent of digital superintelligence as a singularity. That is not to say that it is good or bad, but that it is very difficult to predict what will happen after that point, and that there's some probability it will be bad, some probability it will be good. We obviously want to affect that probability and have it be more good than bad.
Well, let me, on the merger with AI question and the incredible work that's being done at Neuralink, there's a lot of fascinating innovation here across different disciplines going on. So the flexible wires, the robotic sewing machine, the responsive brain movement, and everything around ensuring safety and so on. So we currently understand very little about the human brain. Do you also hope that the work at Neuralink will help us understand more about the human mind, about the brain?
Yeah, I think the work in Neuralink will definitely shed a lot of insight into how the brain and the mind works. Right now, just the data we have regarding how the brain works is very limited. We've got fMRI, which is that's kind of like putting a stethoscope on the outside of a factory wall, and then putting it like all over the factory wall, and you can sort of hear the sounds, but you don't know what the machines are doing really. It's hard. You can infer a few things, but it's a very broad brushstroke. In order to really know what's going on in the brain, you have to have high precision sensors, and then you want to have stimulus and response. Like if you trigger a neuron, how do you feel? What do you see? How does it change your perception of the world?
You're speaking to physically, just getting close to the brain, being able to measure signals from the brain.
Yeah,
will give us sort of open the door inside the factory.
Yes, exactly. Being able to have high precision sensors that tell you what individual neurons are doing, and then being able to trigger the neuron and see what the response is in the brain, so you can see the consequences of if you fire this neuron, what happens? How do you feel? What does it change? It'll be really profound to have this in people, because people can articulate their change, like if there's a change in mood, or if they can tell you if they can see better or hear better, or be able to form sentences better or worse, or their memories are jogged, or that kind of thing.
So on the human side, there's this incredible general malleability, plasticity of the human brain. The human brain adapts, adjusts, and so on. So
that's not that plastic, to be totally frank.
So there's a firm structure, but nevertheless, there's some plasticity. And the open question is, sort of, if I could ask a broad question, is how much that plasticity can be utilized. Sort of on the human side, there's some plasticity in the human brain. And on the machine side, we have neural networks, machine learning, artificial intelligence. It's able to adjust and figure out signals. So there's a mysterious language that we don't perfectly understand that's within the human brain. And then we're trying to understand that language to communicate both directions. So the brain is adjusting a little bit. We don't know how much. And the machine is adjusting. Where do you see, as they try to sort of reach together, almost like with an alien species, try to find a protocol, communication protocol that works, where do you see the biggest benefit arriving from, on the machine side or the human side? Do you see both of them working together?
I should think the machine side is far more malleable than the biological side by a huge amount. So it will be the machine that adapts to the brain. That's the only thing that's possible. The brain can't adapt that well to the machine. You can't have neurons start to regard an electrode as like another neuron, because like neurons just, there's like the pulse, and so something else is pulsing. So there is that elasticity in the interface, which we believe is something that can happen, but the vast majority of the malleability will have to be on the machine side.
But it's interesting when you look at that synaptic plasticity at the interface side, there might be like an emergent plasticity, because it's a whole nother, it's not like in the brain, it's a whole nother extension of the brain. We might have to redefine what it means to be malleable for the brain. So maybe the brain is able to adjust to external interfaces.
There will be some adjustment to the brain, because there's going to be something reading and simulating the brain, and so it will adjust to that thing. But the vast majority of the adjustment will be on the machine side. This is just it has to be that, otherwise it will not work. Ultimately, like we currently operate on two layers. We have sort of a limbic, like prime primitive brain layer, which is where all of our kind of impulses are coming from. It's sort of like we've got like a monkey brain with a computer stuck on it. That's the human brain. And a lot of our impulses and everything are driven by the monkey brain. And the computer, the cortex, is constantly trying to make the monkey brain happy. It's not the cortex that's steering the monkey brain. It's the monkey brain steering the cortex.
But the cortex is the part that tells the story of the whole thing. So we convince ourselves it's more interesting than just the monkey brain.
The cortex is like what we call like human intelligence. So it's like that's like the advanced computer relative to other creatures. Other creatures do not have either. Really, they don't have the computer, or they have a very weak computer relative to humans. But it's like it sort of seems like surely the really smart thing should control the dumb thing, but actually the dumb thing controls the smart thing.
So do you think some of the same kind of machine learning methods, whether that's natural language processing applications, are going to be applied for the communication between the machine and the brain to learn how to do certain things like movement of the body, how to process visual stimuli, and so on? Do you see the value of using machine learning to understand the language of the two-way communication with the brain?
Sure. Yeah, absolutely. I mean, we're a neural net. And that, AI is basically neural net. So it's like digital neural net will interface with biological neural net, and hopefully bring us along for the ride. But the vast majority of our intelligence will be digital. This is think of like the difference in intelligence between the cortex and your limbic system is gigantic. Your limbic system really has no comprehension of what the hell the cortex is doing. It's just literally hungry, or tired, or angry, or sexy, or something. And then that communicates that impulse to the cortex and tells the cortex to go satisfy that. So then a great deal of like a massive amount of thinking, like truly stupendous amount of thinking, has gone into sex. Without purpose, without procreation, which is actually quite a silly action in the absence of procreation. It's a bit silly.
Well,
so why are you doing it? Because it makes the limbic system happy. That's why. But it's pretty absurd, really.
Well, the whole of existence is pretty absurd in some kind of sense.
Yeah, but I mean, this is a lot of computation has gone into how can I do more of that with procreation not even being a factor. This is, I think, a very important area of research by NSFW.
An agency that should receive a lot of funding, especially after this conversation.
I propose the formation of a new agency.
Oh boy. What is the most exciting, or some of the most exciting things that you see in the future impact of Neuralink, both on the science, the engineering, and societal broad impact?
So Neuralink, I think, at first will solve a lot of brain-related diseases. So it could be anything from like autism, schizophrenia, memory loss. Like everyone experiences memory loss at a certain point in age. Parents can't remember their kids' names and that kind of thing. So there's, I think, a tremendous amount of good that Neuralink can do in solving critical damage to the brain or the spinal cord. There's a lot that can be done to improve quality of life of individuals, and those will be steps along the way. And then ultimately, it's intended to address the existential risk associated with digital superintelligence. Like we will not be able to be smarter than a digital supercomputer. So therefore, if you cannot beat them, join them. And at least we want to have that option.
So you have hope that Neuralink will be able to be a kind of connection to allow us to to merge to ride the wave of the improving AI systems?
I think the chance is above 0%.
So it's non-zero.
Yes.
There's a chance, and that's
so have you seen Dumb and Dumber?
Yes.
So I'm saying there's a chance.
You're saying 1 in a billion or 1 in a million, whatever it was in Dumb and Dumber.
It went from maybe 1 in a million to improving. Maybe it'll be 1 in 1,000, and then 1 in 100, then 1 in 10. It depends on the rate of improvement of Neuralink and how fast we're able to make progress.
Well, I've talked to a few folks here that are quite brilliant engineers, so I'm excited.
Yeah, I think it's like fundamentally good. Giving somebody back full motor control after they've had a spinal cord injury. Restoring brain functionality after a stroke. Solving debilitating genetically oriented brain diseases. These are all incredibly great, I think. And in order to do these, you have to be able to interface with the neurons at a detailed level, and you need to be able to fire the right neurons, read the right neurons, and then effectively you can create a circuit, replace what's broken with silicon, and essentially fill in the missing functionality. And then over time, we can develop a tertiary layer. So if like the limbic system is the primary layer, then the cortex is like the second layer. And as I said, obviously the cortex is vastly more intelligent than the limbic system, but people generally like the fact that they have a limbic system and a cortex. I haven't met anyone who wants to delete either one of them. So they're like, okay, I'll keep them both. That's cool.
The limbic system's kind of fun.
That's where the fun is. Absolutely. And then people generally don't lose the cortex either. Right, so they like having the cortex and the limbic system.
Yeah.
And then there's a tertiary layer, which will be digital superintelligence. And I think there's room for optimism, given that the cortex, the cortex is very intelligent and the limbic system is not, and yet they work together well. Perhaps there can be a tertiary layer where digital superintelligence lies, and that will be vastly more intelligent than the cortex, but still coexist peacefully and in a benign manner with the cortex and limbic system.
That's a super exciting future, both in the low-level engineering that I saw is being done here and the actual possibility in the next few decades.
It's important that Neuralink solve this problem sooner rather than later, because the point at which we have digital superintelligence, that's when we pass to singularity, and things become just very uncertain. It doesn't mean that they're necessarily bad or good, but the point at which we pass singularity, things become extremely unstable. So we want to have a human brain interface before the singularity, or at least not long after it, to minimize existential risk for humanity and consciousness as we know it.
So, but there's a lot of fascinating actual engineering, low-level problems here at Neuralink that are quite exciting. What
the problems that we face in Neuralink are material science, electrical engineering, software, mechanical engineering, microfabrication. It's a bunch of engineering disciplines, essentially. That's what it comes down to, is that you have to have a tiny electrode. It's so small it doesn't hurt neurons, but it's got to last for as long as a person. So it's got to last for decades. And then you've got to take that signal, you've got to process that signal locally at low power. So we need a lot of chip design engineers that are, because we've got to do signal processing and do so in a very power efficient way so that we don't heat your brain up, because the brain's very heat sensitive. And then we've got to take those signals and we've got to do something with them, and then we've got to stimulate the back to so you could bidirectional communication. So if somebody's good at material science, software, mechanical engineering, electrical engineering, chip design, microfabrication, those are the things we need to work on. We need to be good at material science so that we can have tiny electrodes that last a long time. And it's a tough thing with the material science problem. It's a tough one because you're trying to read and simulate electrically in an electrically active area. Your brain is very electrically active and electrochemically active. So how do you have, say, a coating on the electrode that doesn't dissolve over time and is safe in the brain? This is a very hard problem. And then how do you collect those signals, in a way that is most efficient, because you really just have very tiny amounts of power to process those signals. And then we need to automate the whole thing so it's like LASIK. So it's not. If this is done by neurosurgeons, there's no way it can scale to large numbers of people, and it needs to scale to large numbers of people because I think ultimately we want the future to be determined by a large number of humans.
Do you think that this has a chance to revolutionize surgery, period? So neurosurgery and surgery all across?
Yeah, for sure. It's got to be like LASIK. Like if LASIK had to be done by hand by a person, that wouldn't be great.
Yeah.
So it's done by a robot. And the ophthalmologist kind of just needs to make sure your head's in the right position, and then they can just press a button and go.